Hey everybody, welcome to the AP Calculus Review Series. This is the first episode, well, the first official episode. This is on Unit 1 for Limits and Continuity. In this series, I'm going to be going through some calculus concepts and really preparing you for the tests throughout the year. I already made a video, that's what I was saying earlier, I already made a video about how the series is going to work, so if you haven't seen that, I'll leave a link in the description to that. And yeah, let's get started. So the way this series is going to work, just briefly, I'm not going to really be working through a lot of problems. I'm just going to give you a good understanding of how we're going to use these calculus concepts and how and why they work, essentially. So we have limits here, but I'm not going to start with limits. Typically in calculus, you start with limits. I'm going to start with the continuity part because I think that's a good way to branch into limits. So what is continuity? Continuity really describes how functions, if they're continuous, okay? And by the way, here, this space, sometimes I'm going to use this, not for this episode, but like if I have important theorems and stuff that I want to put here, I'll put it there. So I'll kind of dedicate a little panel here for that. Anyway, so with continuity, we're talking about if a graph just is continuous. And by continuous, I mean, if it just, if it just continues. That is not a good marker. Alright, so I think we have a better marker now. So by continuous, I mean, there we go, that's a good marker. If it just keeps flowing, like, indefinitely, And you can be continuous on a graph really anywhere. Maybe there's one point where you just break, right? And their function is not defined at that point. So maybe you have a hole there, right? And that's a break in the graph, right? Because if your function is not defined in a certain place, then the graph just stops and it keeps going. It's just that one little tiny point where it doesn't, the function doesn't pass through. So this would be continuous everywhere else because you have points defined everywhere. It's not here, right? So that's what we mean by continuous, okay? So, we can kind of just use this example. So we have different kinds of continuity. I could draw like XY grids. Actually, I will. Yeah, I'll draw XY grids. So basically, so let me move this out of the way. We're not going to need it. But basically, so like what we said. Let's say we have some function, some arbitrary function, right? And it can keep going to infinity. I mean, we're just going to assume it goes to infinity. It doesn't really affect us much. This is continuous everywhere, assuming the endpoints don't, they keep going. This is continuous everywhere, except what if we just break the graph there, right? And then we have, a hole there, right? And the hole, think of the hole as just really, really, really small. It's just, the function is defined everywhere else except that one point. And that, at that one point, maybe it's x equals 5. X equals 4.9999 repeating, and x equals 5.000 repeating with like a 1 at the end, everywhere else, like if you move a little bit to the left or right, it's going to continue, right? So this is a type of discontinuity. Everywhere else you're continuous, but here you're discontinuous, you're not continuous, okay? So that's one type. What's another type? Well, let's say you had a vertical asymptote, right? Let's say our vertical asymptote was here. And it doesn't really matter that my lines aren't the straightest. I know this isn't really, it's a little better. If we have a vertical asymptote, let's say our graph goes like this, and then, we can have a vertical asymptote going like that. I guess I'll just put endpoints here because why not, or, arrows. So yeah, what if we have this, a vertical asymptote? Well, this isn't continuous. Even if this was going up, it's still not continuous. Let me actually draw that. To show like a better argument here. Alright, so what if we had something like this, right? Even though they look like they're going to approach the same value, this is a vertical asymptote, so that means they're never going to touch this line, cross this line, whatever. They're gonna stay, even if they get this close to the line, they're not gonna actually get to the line. So, and on both sides they're not gonna get to the line. So they're never going to touch. So therefore, if the two like sides of our function never touch, then we're not going to have it's not going to be continuous. So this is also another type of discontinuity. Well, I think the third type of discontinuity that we're going to be dealing with, I think this is the most like obvious one, because this is like, oh well, you know, well even like what if you had a point defined here, right? Like at this x value, well, that's still not continuous because I mean you removed it from here and you like jump down and then jump back up, you know, that's not continuous. But here this is interesting. What if we had something? Actually, I don't need these. What if we had something like this, and then we have like an endpoint there, a hole there, and then what if it jumps down to here and it just keeps going, and these two have arrows going there. Everywhere else it's continuous. It's just here it's not, and so that's you know, that's obviously a discontinuity. So yeah, basically, you know, these are discontinuous. So now we should have names for these, right? Because it's always good to have names for things. Well, this is easy. We can call this a jump discontinuity. So we can say jump. Okay. This is, I mean, we have a vertical asymptote. This is called an infinite discontinuity because, I mean, you go up to infinity. These sometimes have other names. I can't quite remember them. I'll probably put them in, like, down here somewhere. I don't know. This is an infinite discontinuity. And this, well, you remove a point, even if you move it somewhere else. This is, you just remove a point from a graph. So this is known as a removable discontinuity. Or I think sometimes it's known as a point discontinuity. These two are sometimes categorized on the AP exam as non-removable, right? What that means is it's just not removable. It's a discontinuity, but it's not like this one. It's one of these. So, you know, if they ask, oh, which one is a non-removable discontinuity, and they give you 4 graphs, you know it's not going to be this one, okay? Or anything that looks like these. So this is the beginning of our discussion to do with continuity, and discontinuity for that matter. Continuity is pretty easy. It's just like, oh, is your function continuous everywhere? Here we're talking about discontinuity, and you know, I could label this x equals 3, x equals 2, you know, x equals 5. You know, it could be anywhere. It doesn't really matter. And so when we're talking about if a function is continuous or not, we're typically saying, is it continuous at a certain point? You know, each of these is continuous everywhere else except here, or here, or here, right? Everywhere else are continuous. So we could have a completely continuous graph, you know, a graph that's continuous at every single point, everywhere. We could have graphs that are this. We could have combinations of all of these. But what we're trying to talk about is a function continuous at a certain point? And so we need language to precisely describe if a function is continuous somewhere or not. So that's what we're going to be developing, and that's going to help us figure out limits. Whenever dealing with continuity, we need precise definitions. So what I did here is I drew a graph with all of our 3 types of discontinuity. So, you know, take a couple seconds to make sure you actually can label these, right? 5, 4, 3, 2, 1. This is jump, this is removable, and this is infinite. And note that there's not a point defined here. That's completely okay. I mean, we could have a point, we could have a little segment of line that's not defined. It's just not going to be continuous there. It's completely okay for our function. It's just not a continuous function at those certain points. So we have our definitions of one definition of continuity with 3 criteria, okay? And these 3 criteria you really have to understand and know for the AP exam. And that's why I'm here. I'm going to help you understand why these criteria are that way. So first, well, let's think about it. So for a function to be continuous, well, I mean, first your point at that function has to actually have like a definition. You have to have a point defined. So here there's a point to find, here there's a point to find, here there isn't, and so if you don't have a point to find, then I mean you it can't be continuous, because like here, like for removable especially, I think this is the best example. If you have a function here and everywhere else is continuous, just not at this point, you remove this one point, your function is not defined there, so it cannot be continuous. So the first criteria is that f of, let me write that a little better. We have f of a exists. Our first criterion is for our function to exist at that point. And note that it doesn't, f can be another function, it could be g or h or whatever. This is just the general case. And a is just the point that we're talking about, the x value, where, let's say this is our a, or this could be our a, or even up here it could be our a, here. So f of a exists here. It exists here, it exists here, not here, and not here. It exists here, just, at these 3 points, it does not exist. So, if f of a exists, that helps us, be able to build, our definition for continuity. Because clearly here they don't exist, so it can't be continuous. Well, you can still have an f of a. What if we had a point for our removable discontinuity just down here, right? F of a exists now, but, it doesn't exist up here. So what we need is we kind of have to build this notion that, okay, well, let me kind of like zoom in here. So let me kind of zoom in from here, and we can talk about this one point here. It kind of like goes down here and then kind of goes back up. This is that point there, and maybe we can have our extraneous point down here. So this is what we're talking about. This is just this little section here that I just zoomed in. Basically, when you're, like the point here has to be the same as the points like here, 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 all the way, and then on the same side all the way that way. So, I mean, this isn't something we've dealt with in algebra. This is something new. We're talking about like whenever you kind of approach this point from either side, you're going to, you're going to have to have the same value here. So this is weird. This is very different than what we normally see. But that's okay, because we can invent math now. I mean, we can't just invent it without any motivation. Like, this is our motivation. We're talking about approaching a point. So we're going to call this a limit. So we're going to call this, let me write a little clearer, a limit. And our notation is going to be lim, just short for limit, as x approaches, I don't know, we can say this is x equals 3, so let's say x equals 3. So the limit as x approaches 3 of our function, so f of x. So the limit as x approaches 3 of f of x. What does this mean? This means when you approach from either side, you approach a certain value. And here that certain value, let's say this is like -2, so we can say, we can actually make this an ordered pair. 3, -2, right? And then down here this can be 3, -4. So the limit, so in this case, if this is our function f of x, let me just make that clear up there. So this whole function is our f of x. The limit as x approaches 3 of our function, of this function, well, it's -2. Even though f of -3 is -4. So what am I saying here? Our point is like the function at x equals 3 is defined to be -4. Like, that's what that point is. If that point wasn't there, then we wouldn't actually have a point at x equals 3. So here at x equals 3, our y value is -4. If you go a little bit to the left or right of 3, it's going to be around -2, and that's what the limit means. The limit as x approaches 3 of f of x is equal to -2. It's going to be about -2. So, it's saying the values of f of x around 3 are about -2. Now, we have this notion of equality here. Well, we're saying it's about -2, not exactly. But as you get closer and closer to -2, let me try to, if you draw like arrows, kind of you're approaching it like that, then you're going to get closer and closer to -2. And at some point, you're going to actually equal -2. And that is the concept of a limit. If this still doesn't make sense to you, there are a bunch of other videos on YouTube that you can talk about limits. I believe 3 Blue, 1 Brown has a good video on that. And yeah, you can search up a bunch of other videos. But this is what I'm saying. We're approaching a certain value. So that's basically what the limit means. So this actually really helps us, because now we can talk about the limits. But what if, like with our jump here, from the left and from the right, our limits approach different values, right? I mean, down here you approach something like, I don't know, I guess -2 again, and up here you approach something like +3. And so from the left and the right, you have different values. So then we say this limit does not exist. So we have notions of where am I going to write this? Let me just erase this so that we can explore a new concept here. So remember, so limit is denoted as lim as x approaches. I'm going to call this value just k, just some arbitrary value, k of f of x. And I'm not really talking about this function, I'm just talking about things in general. Now we can have a left-handed limit and a right-handed limit. Okay, so what this means, so from the left, which is the negative direction, you can have lim of f of x, but this time it says x approaches k minus. So we have a minus in the exponent. This isn't like a k minus, this is a k like to the minus power. What that means is k, but a little bit to the left, just a tiny bit. You can think of this as some 0.000000001, something like that, to the left, okay? And from the right, we have something very similar. So this is going to be a lim of f of x, but instead of x approaches k minus, we're going to have x approaches k plus. So k to the plus power, basically. And so here we have our minus, so the left-handed limit is going to be about +3, like I said, and the right-handed is going to be about -2 or so. So basically, if these two values agree, if they're the same, if they equal each other, then you have your limit. So we can say if lim x approaches k minus, let me make that a little better, of f of x is equal to lim x approaches k plus of f of x, then the limit as x approaches k, not to any particular direction, so that when you're talking about the limit with just k without the minus to the plus, that means from both directions, so that's taking into account both directions, then this exists. So you're saying that if the limit as x approaches k from the left is not equal to the limit as it approaches from the right, then your limit doesn't exist. Your limit exists here because they both approach about the same values here. The limit actually does exist here because you're both, like on both sides, you're going to infinity. This is going to go to infinity, this is going to go to infinity, so the limit is actually equal to infinity. You can have limits equal to infinity. The only issue here is that this does not, like these two values do not approach, these two limits don't approach the same values from the left and from the right, so therefore our limit at this particular point, like we said, I don't know, x equals -2, this does not exist. So we can abbreviate that as DNE if you want. But yeah, so now we can basically talk about things. So we can say, well, the limit has to exist. If the limit doesn't exist, then we're not continuous. So we can say limit. So limit as x approaches a. So remember, because I was using a here, I was just using k as some arbitrary, non-related thing. We're talking about a here. So continuity, I can say that this is continuity at x equals a, just so we're clear on that. So limit as x approaches a of f of x actually exists. Okay, so really what we say here is this limit does have to exist, but commonly one of the criteria that you'll probably see on your AP exam is that the limit as x approaches a minus of f of x is equal to the limit as x approaches a plus of f of x. So that they mean the same thing because of this little statement here. If the two limits on either side are equal, then the complete limit exists. So that's just what this means. And so, okay, this is good. So we have f of a exists, okay? We have that the limits from the left and the right have to be equal. Now what's the last thing? Well, here the limits from the left and the right are equal. F of a also exists. But the thing is that the limits are not equal to our actual function, like the point defined at the function. So our third criteria of continuity is that the limit as x approaches a, I'm not talking about a minus or a plus anymore, I'm just talking about a of f of x is equal to f of a. So I'm saying that, so because f of a exists, and because the two sides of the limit are equal, the last thing we need is that the limit has to be equal to our actual function at that point. So this eliminates all of our possibilities. So each of these, they eliminate different kinds of things. When we have f of a exists, this eliminates some removable discontinuities, not this one, because we have a point there, but if we didn't have this point here, then that would eliminate that removable discontinuity. This removes this one, because f of a doesn't exist here. I mean, we could make it exist. We just put a point there, we can say that's a closed circle. So now this doesn't eliminate that x value from our continuity. This criteria for the limits have to be equal, that eliminates our jumps. Sometimes it'll eliminate an infinite if this side kind of just goes down, you know, that's another possibility. And for these two to be equal, that removes all of our removable discontinuities. So if we did continue to have that point defined there, that would remove this possibility. And so yeah, basically on the AP exam, sometimes they'll ask you, is this function continuous? If not, then why? And you have to state the precise reason. And one thing to note is you can't always just go to this, okay? If you always look for these two first, you have to look if f of a actually exists, and then if the limit actually exists. And if these two, if you know that the function's not continuous, but these two criteria are met, then that's when you default to this third criterion. But yeah, I think that covers everything from Unit 1. I did not cover the intermediate value theorem. I think I'll cover that later on. I just think it's probably better if we put it somewhere else. I probably will cover it at some point, I think, when we go through other theorems and stuff. But I did not go through every single thing you're going to need. I just went through the main things, and yeah. This video's been long enough already, so I hope to maybe keep videos around this length or maybe a little less if possible, but I really want to give you guys solid intuition and understanding for everything that we will cover in AP Calculus. Thank you so much for watching, and I will see you in the next video on this series. Bye guys.